Hello, this is Mr. Flatness, and today we will be investigating numbers to determine if they are prime or composite. We'll start out today's lesson with some vocabulary terms that you need to write in your notebooks. So you'll be able to push pause so that you can take as much time as you need to get all of these terms and their definitions in your notes. We'll start out with prime number, and a prime number is a whole number, and it has to be greater than 1, and the prime number has only one set of factors. It would have the number 1 and then the number that you are looking at. A composite number is a whole number greater than 1 that has whole number factors besides 1 in itself. So some examples that I can give you. The number 3 is a prime number because the factors of 3 are 1 times 3. However, a composite number would be a number like 6 because I can take 1 times 6 as a set of factors, and I also can go 2 times 3. So, difference between prime and composite. The third term is factors, and factors are the numbers that you can multiply together to get a product. So 1 and 6 are the factors of 6, and 2 and 3 are factors of 6. In our next slide, we have divisibility tests, and these rules that I have here are very important when determining if a number is divisible by specific numbers. So please write these down in your notes, as they will be very helpful. So looking at this, a number is divisible by 2 if the 1's digit is even. So that's saying if I have an even number, I can divide it by 2. A number is divisible by 3 if the sum of the digits is divisible by 3. So I would just add up the digits in the number, and if I can divide that by 3, then that big number is divisible by 3. For example, if I had the number 34, the number 34 has the digits 3 and 4. So if I added the digits 3 plus 4, that's 7. And is 7 divisible by 3? No, it is not. Therefore, 34 is not divisible by 3. But another example, if I have a number like 39, and the digit 39, or number 39, 3 plus 9 is 12. Is 12 divisible by 3? Yes. Therefore, 39 is divisible by 3. So, one example and one non-example of how that rule applies. A number is divisible by 5 if the 1's digit is a 0 or a 5. So basically, if a number ends in 0 or 5, it's divisible by 5. A number is divisible by 6 if the number is divisible by both 2 and 3. So if the number is even, because that works for 2, and if you add up the sum of the digits and it's divisible by 3, then the number is also divisible by 6. Two more rules for you to look at. A number is divisible by 9 if the sum of the digits is divisible by 9. So again, I can take a look at the number 81. The number 81 is a 2-digit number, so if I add up the digits, 8 plus 1 is 9. Is 9 divisible by 3? Yes, so 81 would be divisible by 3. And then is 9 divisible by 9? Yes, so 81 is also divisible by 9. And the final rule we have a number is divisible by 10 if the number ends in a 0. So, very important rules, can help out a lot when you're looking at divisibility, and especially when we're working at prime and composite numbers. Again, make sure you have these down in your notes. So in our first example, we want to identify whether a number is prime or composite or not. And we're going to do this by writing all the factors of each number. So, the steps involved are these. To determine if a number is prime or composite, I'm going to list the factors. that I can name for 18, which is my very first number. So I always start at the bottom, and I always make them in pairs. So I know that the factors of 18, I know 1 times 18 is 18. Okay, so I'm going to start out with 1 and 18. So now I'm going to look at 18. I see that it's even. So going back to my divisibility rules, I know that 2 is a factor. So 2 times 9 is 18. Then I'm going to look at the next number. So I started with 1, then I went to 2, and then I'm going to check 3. Well, again, I can use my divisibility rules. I can add up the digits 1 plus 8, that's 9, which is also divisible by 3, so I know then that 18 is divisible by 3. So 3 times 6, I know, is 18. I can check 4, and there's no factor other than, or that goes along with 4, that would give me 18, so 4 would not work. I would also check 5, and the first thing I notice is that the 1's digit is an 8. It's not a 5 or a 0, so I know that 5 is not a factor. And then the next number to try is 6, and I've already listed that factor right here. So therefore I know that I have listed then all of the factors of 18. Some of you might have remembered in 5th grade calling this rainbow factors, 1 and 18, 2 and 9, 3 and 6. Same kind of method. But anyway, the factors of 18 are 1 and 18, 2 and 9, 3 and 6. Because this has more than one set of factors, 18 then is a composite number. Now I'll take a look at 67. Looking at 67, again, I'm going to use divisibility rules. First thing I'm going to notice is that 67 is an odd number. So I know that no even numbers will work. 2, 4, 6, 8, 10. No even number will go into an odd number. So now I'm going to start thinking about some odd numbers. So I'm going to go to my rules. So I'm going to think about 3. The rule of 3, I have to add the digits. 6 plus 7 is 13. 3 does not go into 13. Therefore, 3 is not a factor of 67. I'll check 5. Well, 67 doesn't end in a 5 or a 0, so 5 does not work. I'll try 7. I never shared with you a rule for 7, but 7, and I think about all the basic facts, I know 7 times 8 is 56, and I know 7 times 9 is 63, and I know that 7 times 10 is 70, so therefore 7 is not a factor. 9 is not a factor according to the rules. So when I test all those numbers, I don't really see a factor. The one thing you might try is the number 13, but then when you look at 13, 13 is not a factor either. So therefore all I know is that 1 times 67 are the only factors that I know of that would multiply together to get 67. So therefore I know that 67 is a prime number. To go along with all my rules, the other thing I must have, and that is a firm knowledge of my basic facts and multiplication and memorizing them. Because if you have those facts memorized, it takes problems like these and trying to come up with factors, and it makes it a lot quicker and much easier. Now that I know about numbers and if they're prime or if they're composite, then I can move into another skill called prime factorization, and that is to take a look at a number and find out all of the prime factors that make up that number. So our goal is to take a number, write it as a product of prime numbers. And so again, product means we're going to have multiply in this particular skill. So here are the vocabulary terms you need to write down in your notes for further reference. Prime factorization is writing a number as a product of prime factors. The other thing that we need to do is make a factor tree to find the prime factorization. So that's not a vocabulary term, but that's just a step that we need to use. So I'm sure that in the past that you've worked with factor trees. So in the next example, we're going to show you an example of a factor tree. Here is a process on how we would find all the prime factors of a particular number. So I would write down most of the information, if not all the information, in your notebooks on this slide. So we're going to take a look at the number 450. And what I want to do is find all of the prime factors that make up the number 450. So I do that by making a tree, and you've probably made factor trees before. But just to review, I'm going to take 450 and split that up into a bunch of factors. So I know that 30 times 15 would equal 450. Now, you don't have to choose 30 and 15 if you don't want to. There are many different factors that make up 450. One that comes to mind right away is 45 times 10. So you could also start it out by going 45 times 10. But I just chose 30 times 15. So I'll notice that 30 and 15 are not prime numbers, because I see that 30 ends in a 0, 5 ends in 5, 15 ends in 5. So I can split them up. So I'm going to take 30, and I'm going to say 30 is 6 times 5. I could also say it's 3 times 10, but right now I chose 6 times 5. 15 I have as 3 times 5. So again, your knowledge of your basic facts, knowing what numbers, when you multiply them together, will give you different answers, is so critical here, because it makes this problem go much quicker. Now looking at 6 and the ones that I have, 6 I can break up in 2 times 3. And I know that 2 is prime, I know that 3 is prime, and I know that 5 is prime. So I'm going to just continue and bring down the 5 down to here. 15 we said is 3 times 5. 3 I know is a prime number, so I'm going to bring it straight down. 5 is a prime number, I'm going to bring that straight down. So the prime factorization then of 450, when you get to the bottom of the tree, the one thing that you should know is that all these numbers here have to be prime numbers. So 450, the prime factorization of that is 2 times 3 times 5 times 3 times 5. This is a unique set of numbers. And when I take 2 times 3 times 5 times 3 times 5, the only number that I can get is 450. That's it. There's no other number. So that's a very important thing to know. That's why we want to prime factorize numbers, because it is the root of all numbers here. I know that this is a special set of numbers. And in the real world, knowing prime numbers or prime factorizing numbers, that helps people who make codes or secret codes, or helps them to break secret codes. The final step to do is notice that my numbers are kind of mixed up in a different order. So what I like to do to kind of clean it up is to take a look at putting these numbers in order from smallest to biggest. So 450 would be 2 times 3 times 3 times 5 times 5. And then I could write that even shorter by using exponents. So if I know 3 times 3, I know that is 3 to the second power. I know 5 times 5 is 5 to the second power. So the neatest way and quickest way to write the prime factorization of 450 would be 2 times 3 to the second power times 5 to the second power. In this next slide, I've taken the same number 450, and now I'm going to go through a different method. Factor trees are great, but the one thing that's kind of tricky about factor trees, or that's difficult about working with factor trees, is that it takes a lot of space on your paper to try to find the prime factors of that number, or especially big numbers. So this method, the ladder method, is another way to find all the prime factors of a number, yet its advantage over it would be that it takes up a lot less space. So here we go. With the ladder method, notice I put the 450 and I wrote it down. But instead of making branches like trees, I've created this bracket that goes with it, where it's just simply a line like this and kind of puts 450 in a box. So what I want to do now is try to identify all the prime numbers that go into 450. The numbers that I think about and are using have to be prime. So the first thing I would want to do maybe is to just kind of give you some numbers to think about. So the numbers that I like to use are 2, 3, 5, 7, 9, and 11. I use those numbers because they're all single digit, and I should know all of the basic facts that go with all of those 6 numbers. On occasion, I'll try 13, but there I use long division as 13. Not many people know their 13's facts. It would be good if you did, but that would be another number to try. And finally, 17. And I don't think I've ever gone any higher than 23. So when you take a look at that, those are the first 9 prime numbers, starting with the number 2. So when I look at 450 here, I look at a lot of different things. I see that it's an even number. I see that it ends in a 0. So the first thing I look at is, well, I know 2 will work for sure, and I know 5 will work for sure. So I like to pick the bigger of the 2 numbers. So I know that 5 will go into 450. So then I can divide that out. This isn't a basic extended fact, so I know then that 9 times 5 is 45, and then I'll just add that 0 in there. So I know that 90 times 5 is 450. So then I'll look at 90 and ask myself, is that prime? And it is not. So I will continue on with my ladder. And again, I notice that it ends in a 0, so I know that 5 will work again. So 90 divided by 5 is 18. So now I'll look at 18, and I'll ask myself, is 18 prime or composite? It's composite, so I will continue on with my ladder. So now I'm going to look at 18. I see that it's even, so I know that 2 will work as a prime number that goes into 18. I add the 1 and the 8, so I know also that 3 is a factor. So I'm going to choose 3 as my prime number that goes into 18. 18 divided by 3 is 6. 6 is not prime, so I'll continue on with my ladder. I know that 3 goes into 6 2 times. And looking at 2, I notice that I've finally come down to a prime number. Once I have gotten that far, so that you keep dividing out, I keep dividing until I get to a number that's prime, then I know that I'm done. And here you can see here that I have saved a lot of space. So now the prime factorization then would be the numbers on the outside of the ladder. So 5, 5, 3, 3, and 2. So the prime factorization of 450 would be 2 times 3 to the second power times 5 to the second power. I also want to clean up one mistake. Going through my prime numbers, 9 is not a prime number because 1 times 9 and 3 times 3. So hopefully you picked up that error while you went through that. If not, quickly erase that in your notes, and also write this problem down in your notes, as this will be a very useful tool. It saves a lot of room, and I like using the ladder method a lot better. And I would encourage you to use the same method. You can still use trees, but the more you work with ladders, the more you'll see their benefits. Here's one more problem. I would suggest pressing pause, trying to get the prime factorization of 54, using either the ladder method or also a tree to come up with its prime factorization, and then press play to watch me solve it. The prime factorization of 54 using the ladder method, I will write the number 54, and then I'll start using the prime numbers that I want to see. 54 is even, so I know 2 works. 5 plus 4 is 9, so I know that 3 will also work. So I'm going to choose 3 as my first prime number that I'm going to use. So 54 divided by 3 is going to be 18. And you can use long division to find that out. 18 is not prime, so I know then that 3 is going to be a factor again. I know that 3 times 6, so 18 divided by 3 is 6. 6 is not prime, so I know 3 also goes into 6 twice. I've come to an end because my last number is prime, so therefore the prime factorization of 54 is going to be 2 times, I'm going to use 3 to the third power. Hopefully you came up with that, or 2 times 3 times 3 times 3. Again, notice, to clean it up, I started with the smallest number and then I worked my way to bigger numbers. That concludes today's lesson. As a quick review, you should go over what is prime factorization and what's a method that you can use to find numbers in a prime factorization. We talked about 2. The final thing is why do we use prime factorization? Well, again, we talked about people in the real world use prime factorization for encryption purposes. Okay, anytime that you have important data, okay, on computers especially, where you want to keep that data safe where no one can have it, a lot of times people will use encryption codes to protect that information, and utilizing and knowing about prime factorization helps people with this encryption progress.